up a lattice, you can have each face in one of these two configurations, and if you like, the partition function is given by counting the number of times each face, type of face occurs, n1 for this type, n2 for that type, weighting them accordingly, and then adding in a non-local weight for closed loops. So such closed loops on the lattice are given a weight beta, the loop fugacity. These models are actually built in the plane using the planar Templey-Lieb algebra. This goes back to Vaughan-Jones and, of course, Templey and Lieb. And these are Yang-Baxter integrable. These weights satisfy the Yang-Baxter equation. And then in the continuum limit, the scaling limit, you get conformal field theories. But because there are no local degrees of freedom, only non-local degrees of freedom living in these extended connectivities or polymers, these are models of polymers, percolation, and so on, you get logarithmic CFTs. You can think of this the other way around, that these lattice models are giving lattice realizations of these log CFTs. So this is a tool to study these new kinds, richer kinds of conformal field theories. Because of integrability, we have commuting transfer matrices, and we're interested in degrees of freedom that live on the boundary, so we wish to introduce a boundary. So following Sklian, we can introduce a double row transfer matrix in this way, and I will always fix so that one boundary, the left boundary, is trivial. The loops describing the polymers or percolation connectivities just close on this side simply, but on the right-hand side, this triangle, which represents the boundary condition, carries an extra parameter xi, and the structure of this right boundary will be quite complicated, and this is where the fusion labels S will enter when we construct the integrable boundary conditions. So the Yang-Baxter equation is satisfied. Here it is diagrammatically. And so the Yang-Baxter equation plus the boundary Yang-Baxter equation, which I'll describe in more detail in a moment, these two relations are sufficient to give you commuting transfer matrices and therefore integrability. Since we're working in a diagrammatic setting, multiplication in the diagrammatic algebra is just vertical concatenation of diagrams. So if I want to multiply a transfer matrix by itself, I just place another transfer matrix diagrammatically on top, then consider the compound diagram. These double row transfer matrices satisfy some simple initial conditions, but also a crossing symmetry. So these models have been studied quite extensively by now, and there are many different classes of boundary conditions that you can construct. And unlike the minimal models, the logarithmic minimal models, infinite families of boundary conditions. But the first striking feature is that the central charges of these models are given by the usual formula for the rational minimal models, where p and p prime are co-prime integers, and the conformal dimensions are given by the usual Kac formula. But now you see that the Kac's labels R and S are not restricted to a finite number of values as they are for the minimal models. Now R and S can take an infinite range of values. We refer to this as an infinitely extended Kac's table. In fact, in this Kac's table, these numbers live in the bottom left-hand corner. So you should think of a logarithmic Ising model where you extend R to infinity and S to infinity. In the rational case, we have just a finite number of irreducible representations that close under fusion. Life is much more complicated. The associated Kac's characters to these conformal weights are given by these expressions. So here this is essentially the Dedekind eta function, and Q is the modular norm. The way to think about these characters is that they're just the spectrum generating function for the conjugate RS boundary conditions when you're on the strip, and you have the simple boundary condition on the left, as shown here, and an RS type boundary condition on the right. When you set up such a system and look at the spectrum, you find that the conformal dimension that enters is precisely the conformal weight delta Rs associated with the Rs boundary condition, and this is just a reflection of such conjugation of operators and boundary conditions. Rs equals 1, 1, that lives in the bottom left-hand corner. This is the vacuum boundary condition. These boundary conditions are some natural generalization of boundary conditions that occur for the rational minimal models. In the rational minimal models, you have spins, or more generally RSOS heights. In some sense, the logarithmic minimal models are a special limit where you take the number of heights to infinity. There is a systematic construction of the boundary conditions on the lattice using fusion to construct integrable seams that you then fuse to the vacuum boundary to form the RS integrable boundary conditions. This is a systematic construction, and the Kac labels R and S appear naturally as the fusion levels for the seams that you fuse to the boundary. You can construct an infinite family of integrable boundary conditions of Kac type by simply generalizing the known construction for the rational minimal models, and when you do numerics on finite size strips and extrapolate the conformal data, you reproduce precisely these characters and conformal weights given by these strip conformal partition functions. For those boundary conditions, the Kac labels have integer values. R and S take the values 1, 2, 3, up to infinity. But in various studies of models associated with log CFTs, such as polymers and percolation, people have found that in some circumstances, conformal weights and operators appear where the Kac labels take half integer values. So I should say that LM12 is critical dense polymers, LM23 is critical percolation, LM34 is logarithmic easing. Of course, the central charges here are -2 and 0 and 1/2, corresponding with the regular easing. Of course, this is not a rational or a unitary theory. And so on, and so that LM25 would be the logarithmic Yang-Lee model. In particular, looking at polymers and percolation, Soler and Duplantier in the late 80s found indications that there are conformal weights with half-integer Kac labels R and S. And in 2009, David Ridout suggested that there is a special half-integer conformal weight that plays a role, as described by Watts, for the crossing probabilities in critical percolation. Since a number of authors, in particular Delfino in 2013, have identified further conformal dimensions with half-integer Kac labels that play a role in the CFT description of these logarithmic minimal models. So there are some natural questions that arise. If we can construct the boundary conditions corresponding to integer R and S, can we construct integrable boundary conditions for these logarithmic minimal models conjugate to conformal weights with half-integer Kac labels? So here R is an integer, so R minus a half is a half or odd half integer. Given that there are no local degrees of freedom, how are the boundary degrees of freedom encoded? And we'll see again that they're encoded by these Kac labels R and S, which are integers, but shifted by half integer. So the answer to these questions is, of course, yes, otherwise I wouldn't be presenting this talk. And here I'll show you the boundary conditions associated to conformal weights with half-integer S values. But more boundary conditions should exist. So this is where Raban boundary conditions come in. There's a long history of studying Raban boundary conditions. They occur in partial differential equations and so on. Raban boundary condition is actually a linear combination of Dirichlet and Neumann boundary conditions. Since we have no local degrees of freedom, we obtain matrix representations by acting diagrammatically with our diagrammatic transfer matrix on linked states, mapping back to linked states. So we have a Hilbert space, if you like, or a vector space, more accurately, that we act on with the diagrammatic transfer matrices to form matrix representations. So we need first to fix the vector space of linked states. So a linked state on n bulk and w boundary nodes is a planar diagram of non-crossing arc segments. So these first two, these would be in the usual Temperley-Lieb case of the Kac boundary conditions, but now we allow half arcs to go to the right boundary. It contains D, which is S minus 1, so S is the Kac label. D will be the thickness of an S-type seam later. So we have D defects, which are denoted by vertical line segments, as you see here, here, and here, attach individual nodes to a point above at infinity. In addition, we have B boundary links linking individual nodes to the right boundary. So you can see that there are these boundary links. We need such linked states because we will want to act with the one boundary Temperley-Lieb algebra, which has a non-trivial action on these boundary links. The remaining half into n plus w minus d minus b nodes are connected pairwise by half arcs, such as these. So it specifies the vector space of linked states, and you can work out the dimensionality, and you can separate it into sectors labeled by the quantum numbers d and w, and given by binomials. And the surprise is, if you take these binomials and sum over all values of d, you get 2 to the n. That's not obvious given the expression for the binomial. So the transfer matrix D will act on these Raban states. And again, I stress there are no half arcs joining a pair of boundary nodes. No boundary link emanates from a boundary node. So this red dashed line separates the n bulk nodes from the boundary nodes. And every boundary node is either a defect or linked to a bulk node. So this is how you specify the linked states. Here are some examples where these numbers are n, the number of nodes in the bulk, and w, the number in the boundary, and s is related to the number of defects, which are the vertical lines. And those vertical defects can be closed. This is a matter of taste. They can be closed to an S-type seam on the right by passing under these boundary links. So you can take this, you can take such a defect and close it to the right. Each of these can be closed to the right, and it's just a different way to do the same bookkeeping. Alternatively, you can close these vertical defects to the left. It's a matter of taste. They're all equivalent. So to act on these linked states, we need to introduce the one boundary Temperley-Lieb algebra. So again, this has quite a long history, going back to Nichols et al. In 2005, Martin Salur much before that, 94. And again, this is a diagrammatic algebra, and to the bulk plaquettes or faces, we add one additional generator on the boundary, denoted by a triangle this way, and this generates for us a diagrammatic algebra. So it's the Temperley-Lieb algebra, and now we have various parameters that enter. There's the closed loop fugacity in the bulk, and then there are two kinds of boundary loops that can close on the boundary. So here's an example. The generator corresponding to this triangle acts as the identity everywhere on the left and only has a non-trivial action on the boundary. And when we multiply them together, we identify this loop segment with the one below, and then that generates a half loop, which we remove and give a weight beta 2. And then we close everything up, and we see that we get the generator Fn back again. That's this diagram up to this scalar beta 2. There's another way that it can close on the boundary to give beta 1, but generally we'll take beta 1 equal to beta 2 anyway. So these diagrammatic generators satisfy a number of relations, including the usual Temperley-Lieb relations, plus a couple of additional relations on the boundary. And this is the algebra on which integrability will be built. To describe the boundary vacuum condition, this is the one labeled by Rs equal to 0, a half. Notice that S is now a half integer in this labeling. We take the boundary triangle to be a linear combination of Neumann and Dirichlet triangles. So this one is just the identity. That's why it wasn't a generator. The identity is always part of the generators in our algebra. And this one is Fn on the boundary. So we have the identity in Fn. This linear combination is a combination of two boundary conditions. So this is truly a Robin vacuum condition. So we introduce SKU to be this trigonometric function. Gamma u, this is not the gamma function. This is a special trigonometric function, a special weight we have to give to the first boundary triangle so that this is an integrable boundary condition satisfying the boundary Yang-Baxter equation. It's very convenient to reparameterize everything in terms of trigonometric functions, and then beta 1, beta 2, and gamma can be written this way. R is just a constant, and you see everything is written in terms of trigonometric functions, in terms of u and xi. Xi is a free parameter that lives on the boundary. It's a boundary field. You can think of it as a generalization of a boundary magnetic field. So that's a boundary parameter. In addition, there's a parameter alpha. Again, for numerics, we'll always set beta 1 equal to beta 2, just for convenience. This boundary vacuum condition had already been studied by Jacobson and Soleur in 2008, and what they found was that it's conjugate to the 0, 1 half operator. So if you just formally set R equal to 0 and S equal to half in the Kac formula, you get this conformal weight, and that's what they observed numerically. Yeah, so they're called logarithmic minimal models because of the analogy. For each rational minimal model, there is a logarithmic minimal model, but polymers and percolation have no counterpart in the minimal models. It's certainly not a rational model. It's not an ordinary model. It's non-rational, non-unitary. There is a lowest state, yes. The Virasoro algebra does have an action, but it's not the usual Virasoro. You'll see it's a limit of the usual Virasoro in the way I'll explain. So the first thing to note is that these boundary triangles satisfy the boundary Yang-Baxter equation, so that these are integrable boundary conditions, and we can construct more general S minus a half integrable boundary conditions. So S is an integer, S minus a half is half integer. Using fusion to address this boundary Robin vacuum condition. So here is the usual boundary Yang-Baxter equation presented diagrammatically. These boundary triangles depend on the spectral parameter u and the boundary field xi. And for logarithmic theories, you can have solutions to these equations. So not surprisingly, these are quite complicated objects when they're fully dressed. And this little triangle can be expanded out in this way to construct an RS boundary condition. So the idea is you start with the Robin vacuum on the right, denoted by Rs equals 0 and a half. And then you dress firstly with an integrable seam of S-type. You see, this is very simple. This is just the identity operator. All of the connectivities or polymers just go straight through. But it's non-trivial because there is a fusion projector acting from the lower edge to ensure that none of these loop segments close among themselves. Then there is another seam. This is of R-type, so it's labeled by R1. So this one has W columns. I'll say how W is related to R in a moment. And this is where the boundary parameter xi occurs. So you see we have a spectral parameter here, no spectral parameter there. And here we have inhomogeneities, column inhomogeneities xi k, where you shift, as you increase k, you shift by plus lambda as you move to the left. And you start with xi1 here and xi0 there. And again, you fuse along the bottom edge to make sure that none of these loop segments close among themselves. The loop segments in the R-type and S-type seams are allowed to close between the two, but not within the single seam. Effectively, we take them to plus or minus I infinity, so it becomes the braid or the inverse. So there is no spectral parameter in the S-type seam. That's the way you reproduce. If you take the braid limit where U goes to plus or minus I infinity of the R-type seam, that's how you obtain the S-type seam, and that's how they're related one to the other. I won't describe in detail the implementation of the diagrammatic fusion that you act with on the lower edge, but this is essentially fusion so that when you have two columns, for example, you take a spin half object and you project down onto the spin one object. It's exactly the same type of fusion, but now it's implemented diagrammatically on loop segments, so there are some subtleties. In particular, these projectors ensure that W and D are good quantum numbers for this system, so that we can look at sectors labeled by the widths W and D, and these are in a sense labels replacing the Katz labels, but they're related to S and R in rather simple ways. So the number of defects is actually related to S just by D equals S minus 1, as I said before. The relation between W and R is much more complicated, and actually this arithmetic type formula comes out of studies involving corner transfer matrices. It's not obvious to guess the relation between the R Katz label that you will observe and the width of this seam, but it's actually given by this floor function of the absolute value of R multiplied by P prime on P. The full relation between R and W is given here. So you take this relation and you can deduce this one. It's essentially the inverse, taking into account the fact that W must be positive. So there is some theory behind this relation between W and R, and it was anticipated, and it's confirmed by numerics, as I'll show you later. So we can construct for each boundary condition commuting transfer matrices. So all we need to do is to take the logarithmic derivative at U equals 0, and we will obtain the Hamiltonians. The Hamiltonian in the case where there is no R-type seam, when W is equal to 0, is very simple. It's just given by the expression of Jacobson and Slur in 2008. And you can see that there is this, in addition to the usual Hamiltonian, there's one extra generator that lives on the boundary in the one-boundary Templey-Lieb algebra. So as an operator acting on a vector space, with W and D quantum numbers fixed, it acts from that space back to itself, and that's enforced by the projection operators. The Hamiltonian takes this form. So now we have the width of the R-type seam greater than 0, and this is the expression that replaces this one. And this expression is valid for all cases except for the very special case lambda equals pi on 2, which is critical dense polymers. But fortunately, in that case, the system has been studied in depth and is analytically integrable for arbitrary finite sizes, and everything has been studied in detail in this paper with Rasmussen and Tapunin. Notice that D or S does not appear in this Hamiltonian. D and S only enters through the choice of the vector space of states that you act on. So although the Hamiltonian does not depend explicitly on D and S, the spectrum that you get when you act on the different vector spaces does depend on D and S, or S. Now, the little f here was replaced with a capital F. These are generalized projectors. I say they're generalized projectors because if you normalize them appropriately, the square just gives back Fn. So when W is equal to 0, there is no distinction between little f and capital F, but as you increase the width of the R-type seam, these start to take some non-trivial expressions, and they have some very nice algebraic properties which generalized Temperley-Lieb projectors, or Wenzel-Jones projectors if you prefer. So these have very nice properties, and the C's here are again just trigonometric functions, but now of lambda, and by convention, when you see an En plus W, which is at the very last position, that's identified with the generator Fn plus W. So we want to study the thermodynamics of this integrable system and relations to conformal field theory. So the first objects to study are the non-universal properties, the bulk and the boundary free energies. And we're fortunate that here we can calculate these quantities exactly. So the partition function per site for this model, denoted by kappa u of xi, is just given by the largest eigenvalue. And that satisfies a rather simple set of inversion relations. So kappa can be factorized into a bulk contribution. So this is proportional to the size of the system. The 2 is there because we have a double row transfer matrix. There is a boundary contribution coming from the left Kac vacuum. And then on the right-hand side, there's a contribution coming from the Raban vacuum boundary condition. And then there's an additional contribution coming from the R-type seam. It turns out that the S-type seam gives no contribution. Its boundary-free energy is always 0. And then there's the remaining term. This is actually the conformal universal term, Lu, which can also, in principle, be calculated, but at the moment is beyond our technology to do analytically, at least. Because of this factorization, the inversion relation factorizes. So you have one inversion relation for the bulk, one for the left boundary, and 2 associated with the right boundary, the Raban vacuum and the W seam. In addition to these inversion relations, you must satisfy the crossing symmetry. So these functional equations together are sufficient to uniquely determine the bulk and boundary free energies. In particular, the boundary contribution. So the bulk is just the standard one. It's the same that you would have for Kac boundary conditions because it's, of course, independent of the boundary conditions. But these are somewhat new, and the boundary has several contributions from the left Kac, the right Raban vacuum, and then the WC. So we have to calculate those separately. There are standard tricks using Fourier transforms to solve those inversion relations, and this is what comes out. The calculations are reasonably straightforward except for 2 points. In the left Kac boundary contribution, the naive solution does not extend to the full interval with lambda between 0 and pi, so you need to do an analytic continuation. That's somewhat non-trivial. For the contribution of the Raban boundary condition on the right, the parameter xi appears, and you can see that there is a non-trivial function appearing here. This theta is defined by this little equation here, and you immediately see that that can admit some discontinuities, but nevertheless, you're allowed to have such discontinuities in the boundary-free energy. So this one actually took quite a bit of work to obtain. So the boundary contribution is just this, where now xi w is xi shifted by w lambda, and alpha minus w is alpha minus w lambda. So these non-universal quantities are all known precisely, and that's very important because we will need to extract the bulk contribution, the boundary contribution, and then look at the universal 1 of n corrections to extract the conformal properties. So each eigenvalue of the Hamiltonian has a bulk contribution, a boundary contribution, and then there is the conformal universal contribution from which you can read off the central charges and the conformal dimensions. So in this formula, Vs, which appears here, is just the velocity of sound. So in theory, at least in principle, this system is exactly integrable, so you should be able to solve it analytically. That would require setting up functional equations for the transfer matrices in the form of T and Y systems. And although in principle it's possible, we're still developing the technology to do that. So at the moment this is just beyond our capabilities. And to confirm that we really understand what is going on here and that we have properly constructed these conformal boundary conditions in the scaling limit, we look at the system numerically by diagonalizing small or not so small transfer matrices directly up to sizes n plus w plus d. That's the widths of the R and S type seams, the total being less than or equal to 26. Since the non-universal quantities are exactly, this means that we can get very good numerical predictions for the values of the conformal properties. So here are some typical plots of boundary-free energies. And these are for widths w equals 0, 1, 2, and 3. So for widths w equal to 0, that's the Raban vacuum case. You can see everything is nice and smooth. No surprises there. But as you increase w to 1, you can see there's one jump discontinuity. And then for 2, we have 2 discontinuities, and then 3. And this was quite surprising when we first saw this. But you can see that the agreement between these quite complicated integral formulas and the numerics is very good indeed, even right up to the point of the jump discontinuity. We did extensive numerics for different p's and p primes, that's different models, and for different values of R and S. And this is just a small sample of the many plots that we generated. The most difficult part is the R-type seam as you increase W, and that's what these plots concentrate on. So here I've separated out R positive or 0 on the left from R negative on the right. So R being negative is a new feature that did not occur for the Kac boundary conditions, but appears here. You really need to consider R negative to correctly predict these conformal weights. And again, I should stress that the sign of R is related to the parity of N. So I have to find a formula for you. Where was it? Here. So you can see that the sign of R is related to the parity of N, well, strictly N plus W plus D. So that you have R negative, and to get all the conformal weights, you want to allow R negative. So this is 0 to pi. Yeah, that's a full interval there for lambda. So each rational fraction of pi along this axis represents a different model. And of course, as you vary lambda, those points are dense, and so you end up with these continuous curves from the predictions of theory. And then when you look at particular models, you start to generate points on these curves, and you can see that by and large the agreement is exceptionally good. There's some loss of precision when you go to lambda very small or to values getting closer to pi, but overall the precision is very good and agreement you can be happy with. So this is varying R, but we have similar plots for varying S, and the quality of the numerical agreement is much the same. So that means that we can start to put together CATS tables for these Robin boundary conditions. So this is just one. This is for LM23, that's critical percolation. And you can see in the position 0, 1, so this is R equal to 0, S equal to 1, so that's 0, a half. That's the Robin vacuum of Jacobson and Salur. But now we can populate out the whole of this CATS table where R can be positive or negative and S is 1 or greater. So you just formally use the CATS table and you fill out all of these values. And you can see that there is a periodicity here. So if I move 2 across this way and up 3, you can see these coincide and everything starts again. This is also observed for the CATS boundary conditions. But you need to be careful because coincidence of these conformal weights does not mean that the representations agree. The representations can be different even if the conformal dimensions agree. Now, coming from the lattice, we can, of course, use numerics to reconstruct the full character, not just the conformal weights. Take this form, where these conformal weights are given by these half-integer values. But then what we find numerically is that the full character is just given by multiplying the usual term with 1 over q infinity here. And you see that this is just the Virasoro-Verma character. Which is not to say that this is the Verma module. You can have quite different representations coming in. So again, we check this numerically by looking at the first 7 to 20 eigenenergies in many, many different cases. And in all cases, by looking at the degeneracy of the excited states, we confirm that you see precisely a spectrum consistent with the Virasoro-Verma characters. So we conjecture that this is... Yeah, of course. That's why we guessed it and we confirmed it. And so as far as the character goes, it's exactly what you expect. But there's a big question underlying exactly what the representations are here. So you might expect that these are all irreducible, but probably there are Feigen-Fuchs modules and so on. So as far as the character goes, it's fairly straightforward to guess it, but the detailed structure has not yet been explored. So we look at finite-sized matrices. We get accurate values for the first so many eigenenergies, and they're close to integers. And we can see the degeneracies of the first so many levels, 7 to 20, building up. And they agree with the partition numbers that come out of expanding 1 over q infinity. That's numerical. But as Paul says, for theoretical reasons, this is exactly what you would predict. And that's what's confirmed numerically. Not yet, no. No, this is not an analytic result. Further to Paul's comment, I should point out that all of the values here correspond to special values. So all of the values here, you cannot say for sure that they're going to be Verma characters, right? These exactly coincide, as I'll point out later, with the conformal weights for the CATS. Because P is even and P prime odd, these exactly coincide with the values for the Kac conformal weights, and we know there that you have characters which are not given by Verma characters. So this is why it's non-trivial. You can have many of these weights occurring which are not the generic ones that you'd associate with irreducible Verma characters, Verma modules. From the lattice, you have a finite size transfer matrix, so you can actually look at a finitized character. So by finitize, these actually encode finitely truncated sets of the integer conformal energies of the infinite system. Such finitized characters appear in corner transfer matrices, and they also occur whenever you look at spectrum of finite double row transfer matrices. And in this case, you remember this binomial in counting states from from my early slides. Now this is just a Q binomial instead of a Q. And when you use a Q binomial, this gives correctly the finitized characters. So that's also a very nice observation. So when you set Q equal to 1 in here, it just reproduces the correct counting of states. Moreover, if you take n to infinity in this expression, then this becomes 1 over this Q infinity, so you reproduce the full Virasoro Verma character. Let me try to explain the relation between what we're seeing here and rational minimal models, height models. It's most easily seen in the context of the Kac boundaries. So let's go back to the Kac boundaries. And you can start with the minimal models, and you can take a limit where m and m prime go to infinity. Now, of course, you need to take this limit through a where m and n prime are prime at each step. You can take the limit so that m prime on m approaches p prime on p, and for technical reasons we need to take that limit from above to maintain the correct ground states for these systems. So this is a symbolic limit. It's taken after the continuum scaling limit. So this is the limit not taken on the lattice models, but taken on the CFT. And this idea goes back to Rasmussen in 2004. If you look at the conformal data for the usual rational minimal models, that's in the left column here, you can take this limit. Now you see that these expressions, for the most part, are homogeneous in m and m prime. So if I take the limit of this one, each m is just replaced by p and each m prime by p prime, and you can start to understand why the expression for the central charges is exactly the same. Of course, for minimal models, must be at least 2. But for logarithmic minimal models, p can be 1. So you can get values here that don't occur there for the allowed values of m and m prime. Similarly, if you take the expression for the conformal weights, these are again homogeneous in m and m prime. So if you take this logarithmic limit, you just replace m with p and m prime with p prime, you get this expression, and that's again precisely the Kac formula, the same formula, but now giving the conformal weights in the infinitely extended Kac table of the logarithmic minimal models. And lastly, you can do the same thing with the Virasoro characters. Here they are. You just formally take this logarithmic limit. The modular gnome q is less than 1 in modulus. So a large positive exponent, that just goes to 0. And if you look carefully, the only term that will survive here is when k equals 0, you get 1. And here, when k is equal to 0, you get r by s. All the other terms will disappear in the limit, so you're left with the Kac character. So this is the sense in which I was saying that the logarithmic minimal models, formally at least, coincide with a special limit of minimal models where you take the number of RSOS heights to infinity. So the number of heights is given by m prime minus 1. The Robin boundary conditions are somehow the analog of the limit of free boundary conditions rather than fixed boundary conditions. So you need to take a little more subtle limit. You take m and m prime to infinity, such that m prime m goes to p prime on p, but now you have to fix parity for m and m prime as you take that limit. And there are three choices. You're not allowed m and m prime both even because they must be co-prime as you take the limit. And when you do that, you take this limit of the Virasoro minimal characters, you get precisely these Verma characters. So this is a nice way to think about how you get these Verma characters out. It's just taking this limit way. So what you're doing is taking a limit where the rational Kac table is very large, but instead of fixing yourself near the edges, you now fix yourself in the middle of the Kac table as you take the limit. And this first limit gives us integer s. That's what I've been describing here. But if you take other parities, you can get half integer r or half integer r and s. So this suggests that we should be able to find boundary conditions for these other two cases. And we're working on it, but so far without success. But there are strong indications that these should exist, and this suggests that they're not far away, that we should be able to find them. I should point out that there are coincidences, as I said before, in the case of percolation between the Kac conformal dimensions and the Raban ones. In the case p even, p prime odd, which includes percolation, there are these correspondences. So a half integer s conformal weights actually coincide as a set, not individually position by position, but as a set. If you look at all the distinct values here, they coincide with all the distinct values there. Likewise, in that case, if r and s are both half integer, they correspond to r being half integer, and so on for the other parities. So this is a rather curious observation, and it tells you you're going to have to think very carefully about the representation theory. So let me summarize. What have we seen? So we studied general logarithmic minimal models on a strip of n columns with Yang-Baxter integrable Raban boundary conditions. So the boundary conditions were actually introduced in the earlier paper on critical dense polymers in 2014. The RS Raban boundary conditions are constructed using R and S type seams. So these are the labels that encode the boundary degrees of freedom. These are just the width of the integrable seams. W and D are the widths of the integrable seams of type R and S that you use to construct the RS boundary condition. The R-type seam admits an arbitrary boundary parameter, which you can vary. In the numerics, we fixed it to -1/2 lambda. This was a convenient value. As long as you stay within a certain basin of attraction, the conformal dimensions do not change as you vary R. If you just keep it real in a certain interval, the conformal dimensions do not change. However, if you scale this with an I log n and take as xi the imaginary part of xi therefore to infinity, you can actually induce a renormalization group flow between various boundary conditions. So this actually plays a role there. The associated boundary conditions are labeled by half integer s, and they're organized again into an infinitely extended Kac table. So now we have two infinitely extended Kac tables associated with these models, but still we're not done. The question of classification of all possible boundary conditions for logarithmic minimal models is an open question. So far we've been concentrating on infinite classes of interesting boundary conditions. Here are the relations again between R and S and W and D. We were fortunate that the exact non-universal Balkan boundary free energies could be obtained analytically by solving inversion relations. So that's quite a non-trivial business, and is an interesting result in its own right that we can calculate this infinite number of different boundary free energies for an infinite family of models. Using finite size corrections in a sequence extrapolation out to quite modest but modestly large sizes, we could predict the conformal spectrum numerically. And we find precise agreement with the theoretical predictions. So of course we had to use a lot of tricks to get out to this size, including sparse matrices, dispatch tables, and in the extrapolation we used Vandenbroek-Schwarz extrapolation, and for the numerical diagonalization we used the anality method and so on. So there's quite a few tricks to get out to these sizes. It's not entirely trivial, even using Mathematica. So the RS Robin boundary conditions are conjugate to operators with half-integer values in this infinitely extended Robin Kac table. So indeed, the degrees of freedom are encoded by R and S, the labels of the construction of the boundary condition. The level degeneracies of the first 7 or 20 levels support the conjecture that these characters are just the Virasoro-Verma characters, but there are many open questions about the precise nature of the associated representations. It remains to find the Yang-Baxter integrable conditions conjugate to the other cases when R is half an integer or R and S are both half integers. And of course, it also remains to do the hard work of solving and setting up the T and the Y systems to obtain all of these results analytically. So I thank you for your attention.